Okay, we're completely bypassing the fluff today. You are staring down the barrel of a high-stakes Cambridge IGCSE Physics exam, paper 0625. And listen, today's explainer, it isn't about generically reading textbook definitions to you. No, we are performing a topper autopsy. We're going to dissect exactly why top-tier answers score maximum points and why ordinary answers just completely crash and burn right at the grade boundary. We're jumping straight into the deep end of measurement, units, and exam strategy to make absolutely sure you never lose these easy marks again. Let's get into it.
So, take a look at this exact exam scenario. You're asked to calculate the area of a rectangle. The length is 20 centimeters and the width is 10 millimeters. It seems like a ridiculously simple calculation, right? I mean, you just multiply length by width and you're done. But here's the thing. This specific trap catches out thousands of students every single year. They see the numbers, they kind of panic about the ticking clock, they grab their calculators, and they fall right into a pit that was engineered perfectly by the examiners.
If you just multiply those together and write down an answer of 200 centimeters squared, you've just lost almost all your marks. You score maybe a 2 out of 10 for simply knowing the basic formula, and that creates a serious grade boundary risk. You'll walk out of the exam hall thinking you completely nailed it, but you've actually just bled crucial points. But don't worry, because by the end of this explainer, you're going to know exactly how to unlock the top-band answer to this exact problem, and more importantly, how to apply that top-tier thinking to literally every calculation you encounter.
Okay, let's dive into this. Why does ordinary revision completely fail? Well, most students spend hours and hours memorizing equations. They make endless flashcards for things like area equals length times width, or speed equals distance divided by time. But honestly, memorizing the equation is completely useless if you ignore the international SI units. Equations only work when the data fed into them speak the exact same mathematical language. If you don't understand the strict rules of unit consistency, your perfectly memorized equation is going to generate a completely flawed answer. The Cambridge guidelines actually outline these painful mistakes very clearly. They specifically warn that failing to grasp units leads to a catastrophic domino effect of errors throughout your entire paper. You might forget missing units in your final answer. Or maybe you round off a number way too early in a complex multi-step calculation. You might provide vague explanations, mix up your graph axis scaling, or just substitute completely wrong variables into the right equation. And the result? It leads directly to conclusions that are totally unsupported by your data. The examiner basically has no choice but to penalize you heavily.
Now, the absolute foundational math skill for IGCSE Physics is choosing the correct unit for a variable. The examiners consider this totally non-negotiable. I mean, before you calculate the resultant force on an object, before you figure out the kinetic energy of a moving car, and definitely before you analyze some complex parallel circuit, you have to master unit consistency. It is the absolute bedrock of every single high-level physics answer you're going to write.
So, let's break down the rules of the game. Using the same units means we can compare the size of variables easily and accurately. And that's exactly why the international SI system was agreed upon in the first place, to create a universal scientific language for all of us. For length or distance, the base SI unit is the meter. For mass, it's the kilogram. For time, it's the second. Every single formula and advanced concept in your entire syllabus builds outward from this specific foundation.
But here is where the stakes escalate. The source material issues a massive "look out" warning regarding derived units. You really have to be careful here. When distance and time are measured in meters and seconds, the speed you calculate must be a derived unit of meters per second. It absolutely cannot be in kilometers per hour. It's called a derived unit because it's mathematically built from those base units, literally the number of meters traveled in each individual second. Mixing kilometers with seconds or meters with hours is a guaranteed way to sabotage your final grade on what could have been a perfect paper.
And fluency in these other SI units is just as critical to prevent marks from slipping through your fingers on those really complex calculations. Force is measured in newtons, energy in joules, power in watts, temperature in degrees Celsius. When you're hit with an intense 6-mark calculation question late in the exam, say calculating the power output of a motor lifting a heavy load, your brain should automatically be checking if your substituted numbers align perfectly with these exact SI units before you even touch your calculator. To never miss these points, you need an unbreakable system. So here is our structured answer framework: concept, evidence or data, scientific reasoning, and finally, examiner wording. Now in a moment, I'll show you the exact examiner clue that changes your calculation completely, but first you need this 4-step framework that makes that clue obvious. First, you identify the physical concept. Then you extract the data from the prompt.
You apply your mathematical reasoning, and then you state your answer using the precise wording the mark scheme demands.
Let's revisit our setup from the beginning. I want you to actively engage right here. Just pause for a second and try to spot the error before a student mistakenly calculates 200. Look really closely at the data provided in the scenario. The length is 20 centimeters. The width is 10 millimeters. The concept we're using is area. The reasoning is multiplication. But the data is mismatched. Do you see it?
The golden rule is this. In a calculation, the units you use must match. They have to be consistent with one another. Length and width absolutely must have the same units before you even think about multiplying anything. You can't multiply apples by oranges, right? You can't multiply centimeters by millimeters and expect the clean, mathematically valid unit of area to just pop out the other side. The universe of physics demands consistency first.
So here is exactly how that golden rule builds a perfect top band answer. Step 1. We identify the mixed units in the data. We've got centimeters and millimeters. Step 2. We apply scientific reasoning to make them consistent. So we explicitly convert the width from 10 millimeters over to 1 centimeter. Step 3. Now and only now do we actually execute the calculation. 20 centimeters multiplied by 1 centimeter equals 20 centimeters squared. This step-by-step logic, proving your awareness of the units, is exactly what the examiner is hunting for.
And honestly, the exam is going to push you much harder than just millimeters to centimeters. Notice the escalation here. To convert centimeters to meters, sure, you divide by 100. But to convert an area, centimeters squared to meters squared, you have to divide by 10,000. And for volume? Centimeters cubed to meters cubed requires dividing by 1 million. Imagine you get a 6-mark density question. If the examiner asks for density in kilograms per cubic meter, but hands you mass in grams and dimensions in centimeters, you have to execute multiple layers of conversion before calculating. Memorize these conversion factors, guys. They are absolute lifesavers. This right here is the difference between a panicked guess and a deliberate top-band strategy. Simply recognizing the trap, explicitly showing the conversion of 10 millimeters to 1 centimeter, and matching the units transforms a failing answer into a definitive success. The math in the top band approach is actually simpler to execute. I mean, it's just 20 times 1, but the underlying physics reasoning is miles ahead, and it demonstrates true mastery of the syllabus. This top band answer succeeds because it checks off every single requirement of our examiner-style correction framework. It uses the correct terminology, explicitly states the method and the formula. It substitutes values with matching units, and crucially, it checks the final answer for reasonability. 20 square centimeters makes logical, physical sense for the dimensions we were provided. 200 square centimeters simply does not. Now, your calculation is mathematically perfect. You've secured the calculation marks. But here is the final provocative thought I want to leave you with today. What if the command word wasn't calculate? What if the examiner asked you to evaluate the data or describe the practical investigation instead of just calculating the area? Well, this exact same mathematical answer might suddenly drop bands because different command words trigger entirely different mark schemes. Mastering unit consistency is really just step 1 of your exam strategy. To understand how exam command words actively change what the examiner wants to see, and to secure those absolute top marks across every single question type, you need to watch our next explainer on timed answer writing systems. It is the mandatory next step to mastering paper 0625. You really don't want to miss it. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. See you there!